What's up, y'all? So about half of what I recorded for this was corrupted when I transferred it to my laptop, so this video won't seem complete. I'll try to fill in the blanks as best as possible. Thankfully, chlorinations aren't particularly complex, so it should be fairly easy to explain. I'll be synthesizing 1,4-dichlorobenzene, or it's para-dichlorobenzene, which I'll refer to as p-DCB from now on. From benzene, I'll be synthesizing p-DCB by electrophilic aromatic halogenation with chlorine gas and a catalyst. Well, a couple different catalysts. p-DCB is a precursor to a compound I intend to synthesize in a future video. I could have easily just bought it because it's very common, as it's used in urinal cakes as a deodorizer and a disinfectant. It's also used in mothballs as a replacement for the allegedly more flammable naphthalene, even though they're both fairly flammable. I decided to both synthesize it and buy it because the chemistry is worth exploring, but I don't know what the yields will be in the reactions I'll be using it for, so I don't want to run out, and it's super cheap. My benzene is also precious to me, so if I can avoid or minimize using it, I will. I do 2 runs using iron and sulfur as catalysts, the first run using steel wool as the source of iron, and the second one using iron filings. I think they're 80 mesh. Steel wool is a little more readily available than iron filings. I have both, so I decided to try both. I recrystallized my commercial 99+% sulfur from xylenes, modifying a procedure in a video from the channel Doug's Lab, which I will link in the video description. I have a book on sulfur, a data book really, that covers solubility tables in organic solvents, amongst other things, including for para and metaxylene. So I did some maths, guesstimation, and ended up using 400 milliliters of boiling mixed xylenes for 75 grams sulfur. Doug used 500 milliliters for 50 grams, and I think he avoided heating above the melting point of sulfur, which is a little over 115 degrees, since mixed xylenes boil at about 138, 139 degrees. I didn't find it necessary to stay under sulfur's melting point, but boiling xylenes are a huge fire hazard, and he did it inside his lab, which is ventilated. He has sort of fume hood set up, I think. Well, I did it outside. His caution is warranted given it was done indoors and he has a wooden lab bench. I did it on a concrete pad, which isn't really flammable as far as I can tell, and it was like 20 degrees below the flash point of xylenes, so I could forego most of the precautions. Doug's Lab is a great channel worth checking out. He hasn't posted in years, which is kind of sad, but he's busy, which is good in general. The chlorine was generated from TCCA, which is trichloroisocyanuric acid, which is commonly available as pool chlorinating tablets. There have been many videos on chlorine generation using these tablets. Adding hydrochloric acid to these generates fairly pure chlorine. After the first 2 runs with iron sulfur catalysis and chlorine, I remembered reading something from the EROS, Encyclopedia of Reagents for Organic Synthesis, for TCCA, went back to it, and found the paper. It used TCCA as a chlorinating agent and several different catalysts, but only 2 when chlorinating benzene. Ferric chloride, which for whatever reason I don't have, and then the other one, which is higher yielding, oddly enough, is 50% aqueous sulfuric acid, which I could easily make. Luckily, the sulfuric acid catalysis has like an 80% yield relative to the 64% yield of ferric chloride. Those are the reported yields, so I used that procedure for the 3rd run. If I had done fractional distillations between runs, I'd have been able to determine yields from the iron and sulfur catalysis, but I did not. There would have been a lot of mechanical loss in the fractional distillations, and I didn't want that. I did do a 2nd run of the TCCA sulfuric acid method to both check the reported 80% yield and because I need chlorobenzene for a separate project. I'll talk more about the 2nd run later. Anyway, we're going to get right into the synthesis. I'll also go over the mechanisms later. These are all the reagents. This is the setup. It's very compact because I was using all my other ring stands at the time. I diluted the hydrochloric acid a bit and started dripping it onto the TCCA to begin the chlorine generation. The chlorine passes through the wash bottle containing concentrated sulfuric acid, so it dries it. I dry it because the ferric chloride and or sulfur chlorides that I'm pretty sure are forming upon reaction with the chlorine, even when it's in an ice bath, are water sensitive and any water will affect the catalytic effect they have. The ice bath is there because the reaction is exothermic and the temperature affects the ortho and para ratios of any dichlorinated product. The black tubing that the chlorine passes through is a fluoroelastomer. It's, quote, like Viton, end quote, made by Duda Energy. All my other non-glass tubing will be disintegrated by chlorine like most rubber or plastic tubings, so I have to use this kind. The adapter that leads into the reaction mixture is made of PTFE, or Teflon, and is actually for thermometers, but I just used a 6mm glass tube. Yields could have been improved by using a fritted gas bubbler, but I don't have one. So once the chlorine starts to pass through the reaction mixture, you will see some white smoke. That is hydrogen chloride that's produced when chlorine reacts with benzene. It looks like white smoke because there's water vapor in the air, and it's forming hydrochloric acid fumes. One part of the footage I lost was holding pH paper over the condenser, and it immediately turns red when it comes into contact with the vapors. So I temporarily took the flask out of the ice bath to sort of jumpstart the reaction. I think the iron sulfur catalyst isn't as active as the typical Lewis acid catalyst like ferric chloride, aluminum chloride, so I found the jump starting fairly helpful. After the reaction was done, I filtered the mixture from the steel wool, washed it with a little benzene, and tried to do a short path distillation to fractionate it. This didn't work without a good fractionated column, so I combined what I distilled and moved on to the second chlorination with iron filings instead of steel wool. Most of that footage was lost, but it's identical to that of the steel wool run. Onto the TCCA sulfuric acid run. I assumed it was 50% sulfuric acid by weight, so I mixed 70 milliliters of water with 39 milliliters of concentrated sulfuric acid. I assume it's 98%, that's why I used 39 milliliters. I added the distillate from the previous runs to the diluted sulfuric acid and then added the TCCA. The temperature was kept from 65 to 80 degrees, which is a little annoying to do, so it's a lot easier to reflux something or stir something at room temperature, but warming it at a specific temperature between like ambient temperature and reflux and holding it there for 5 hours is kind of annoying. It's especially annoying when it's done with just a heating mantle, not like an oil bath or a water bath. It did take some babysitting, but it eventually worked out. Afterwards, it was filtered, layers were separated, the organic layer was dried with magnesium sulfate, and it was filtered directly into what was left in the flask from distilling the iron-sulfur catalyzed chlorination mixture. So I washed all the containers containing anything chlorinated out with some DCM and filtered that into the same flask. I then fractionally distilled the whole mixture with a proper setup. I collected 4 main fractions, one up to 80 degrees, which was mostly DCM, a little benzene, one between 80 degrees and 128 degrees, which was mostly benzene and a little chlorobenzene, one between 128 and 150 degrees, which was mostly chlorobenzene, and the last one between 150 degrees and 180 degrees, which was ortho and para DCB, but probably some chlorobenzene too. O and P DCB boil at 180 and 174 degrees respectively, so they can't really be separated by fractional distillation on this scale. However, ODCB is a liquid at room temperature, so is MDCB, and PDCB is a solid at room temperature, as you can see by all the crystals that clogged in the condenser. So it was easily removed by washing it out with DCM. Now some ODCB did like stick to the p-dichlorobenzene, but there's an easy way to purify it and I'll mention it in a second. But at this point, my entire lab area smelled like straight up urinal cakes, and it took like a week for the smell to completely go away. The last fraction did look substantial, but it was mostly p-dichlorobenzene dissolved in chlorobenzene and ODCB that co-distilled, and when I purified it by fractionally freezing it, barely any liquid passed through the filter, so I just chalked it up to a trace amount of ODCB. Due to the corrupted footage, I summarized what I did just to make it 100% clear, or try to at least. I did a second run of the TCCA sulfuric acid procedure, but I only got a 42.9% yield of chlorobenzene, not the 80% reported yield. I let the temperature get too high, which was obviously my fault, but I was using a different heating mantle and it didn't babysit it well enough, so that definitely lowered the yield. I didn't feel like doing it again, so the range of the yields is factored into the calculations of chlorine absorption. What next? Further chlorinating the chlorobenzene with a different catalyst this time. I could use aluminum chloride by itself, but because ferric chloride is a prototypical catalyst, it was hard to find a paper with a procedure using aluminum chloride alone. What I did find was an interesting paper using an aluminum chloride nitromethane complex as a catalyst. I slightly altered the procedure because it was primarily investigating competitive chlorination and the kinetics behind them. What I did was make it non-competitive by using chlorobenzene alone. Part of the corrupted footage included me showing the reagents used, so I will just list them out here instead. I used all of the chlorobenzene, which was 50 grams, and I used 5.92 grams of aluminum chloride, and then 2.71 grams of nitromethane. I used a little more than that because it was a 96% spectrophotometric grade, and it's essentially 10% by mole catalyst with respect to the chlorobenzene. And then enough TCCA hydrochloric acid to generate half a mole of chlorine in those quantities right there. I always use an excess of acid. This reaction went much more by the book. Heat was evolved to the point that the cooling water, starting at 15 degrees-ish, hit 35 degrees by the end of the addition of the chlorine. Hydrogen chloride visibly off-gassed significantly more than in the iron-sulfur catalyzed reactions. Not just as the white hydrochloric acid fumes, but as significant bubbling from the reaction mixture. After the chlorine addition was completed, water was added to quench the anhydrous aluminum chloride, and everything was added to a separatory funnel. The bottom layer is organic, chlorobenzenes and dichlorobenzenes are denser than water, the top one's aqueous. I am not completely sure why the organic got significantly lighter when I washed it with water, because the water layer stayed the same color, but I'm always glad when something that's supposed to be clear isn't brown anymore. I did a short path fractional distillation on the magnesium sulfide dried, filtered organic layer with an air-cooled condenser instead of a water-cooled one. The lowest boiling compound of the crude mixture is chlorobenzene, which boils at like 131 degrees, so air cooling is sufficient. This condenser is one of the more expensive pieces of glassware I own, so I try to minimize subjecting it to thermal stress. I'll show the fractions in a little bit. What I meant when I said I fractionally froze it is I put the O and PDCB mixtures in the freezer, waited for them to solidify, and filtered them on this fritted glass funnel. At typical freezer temperatures, ODCB is a solid, so the resulting O and PDCB mixture is mostly heterogeneous. The ODCB slowly melts and passes through the filter, minimizing the solvation of PDCB by it. I was pleasantly surprised how well this worked. The melting points of both PDCB products collected were 54 to 55 degrees, very close to the literature value of 53.5 or 54 degrees. Any MDCB that was produced in the chlorination was also removed by this fractional freezing filtration because it is a liquid at room temperature, and actually at freezer temperatures, but again, it was removed by the filtration. After all that, here is what I got. On the left, the iron sulfur and TCCA sulfuric acid chlorination products, excluding the chlorobenzene that I cycled forward. And then on the right are the aluminum chloride nitromethane chlorination products. In the middle, those two vials, and it's just leftover gunk, kind of tarry crap that I couldn't isolate anything from. I'll put in a slide listing out the weighed products from left to right. The main things I care about are the vials containing white solids, which is the p-dichlorobenzene. The recovered chlorobenzene I can combine and use in the other project I mentioned that I was going to use some chlorobenzene for. I don't have any use. I can't think of anything. I looked it up, couldn't find anything. Any use for ODCB. If you have any ideas, let me know. From this, you can probably see that the first runs with iron sulfur and TCCA sulfuric acid, the para to ortho ratio is significantly higher than that for the aluminum chloride nitromethane run. This checks out based on the data reported in both the papers I pulled the procedures from. So I could have made or bought some anhydrous ferric chloride to use as a catalyst, but there are already videos out there that show it used in chlorinating benzene, so I thought I would try something different. Again, I'll link the papers that I base these procedures on. Lastly, I'm gonna go over the mechanisms that I actually know. My chalkboard looks messy, but it was the best way I could show everything that I wanted to. Sometimes ChemDraw is a lot more time consuming than, just drawing it out. If you follow my cursor while I talk, it should all make sense. Up top, I'm assuming what's happening with the iron-sulfur catalysis is the iron is reacting with the chlorine, and because it's excess chlorine, it forms ferric chloride rather than ferrous chloride. Ferrous chloride can become further chlorinated, oxidized to make ferric chloride. Then the ferric chloride is attacked by elemental chlorine, and then it complexes, making this. It's a ferric chloride-chlorine complex. And then one of the double bonds of benzene attacks this chlorine right here, and then this bond between those, the elemental chlorine, goes here to make this, neutral. There is a intermediate, this guy right here. It's a carbocationic chlorocyclohexadiene type intermediate. So this intermediate is delocalized. Like these right here do the same thing, except I'll show a diagram that would explain this specifically, and where E is the chlorine. And yeah, it's delocalized. It's not completely aromatic, obviously, but the hydrogen right here in the intermediate is quite labile, is attacked by the fourth chlorine in the tetrachloroferrate complex, and the carbon-hydrogen bond moves to neutralize this carbocation and make it an aromatic system again. Then it goes over here, you get chlorobenzene, hydrogen chloride is released, regenerated, and ferric chloride is regenerated because it's catalytic in its effect. Honestly, I really don't know what sulfur's role is. I know, not in the case of ferric chloride, obviously, but if there's aluminum chloride and disulfur dichloride, because I assume sulfur chlorides are formed. It's mostly based on the color change of the solution. But if there's aluminum chloride and disulfur dichloride, the benzene is cross-linked in a Friedel-Crafts type reaction to make diphenyl sulfide. Obviously, like I said, this doesn't happen here with the ferric chloride. It just doesn't act in the same way. So I really don't know what sulfur is doing in all of this. And then for the TCCA sulfuric acid mechanism, also no idea. I'll link the paper that the procedure is pulled from. It mentions that it forms some charge transfer complexes with electron donor compounds, so I could see like ferric chloride and complexing with it, and that complex reacting with benzene in the same way that this complex reacts here, but I just don't see aqueous sulfuric acid acting the same way. So, I mean, I guess I could see the free proton acting as the Lewis acid, but it didn't really state that in the paper, and I don't know for sure, so I'm just speculating here. So for nitromethane's role in this aluminum chloride catalyzed reaction, I also don't know. Does it make it a more reactive complex? Maybe. I don't know. It reacts regardless, so it works. If you have any thoughts, or if you know mechanisms of the roles of sulfur and nitromethane, let me know. For now, I'll just move on to the chlorination of chlorobenzene. Chlorobenzene is less susceptible to chlorination than benzene is. This is because halogen-substituted phenyl groups are slightly deactivated to further substitution reactions. Halides are a little weird, unusual, because generally speaking, deactivating groups are meta-directing, but halides are ortho-para-directing. What this means is that when suitable catalysts or reaction conditions are used, the products are primarily ortho and para-substituted. It is ortho and para DCB in this case. meta TCB is formed, but the amount is negligible. So the mechanism is nearly identical to that of the chlorination of benzene, but the intermediates are different. There are two possible positions for ortho, here, meta, here, or only one for pair substitution. The intermediates partially explain the weird in-between behavior of halide groups in aromatic substitution reactions. In an analogous reaction with aniline, there would be an extra intermediate for the para and ortho substituted product, but there is not one for meta. The starred ones represent, I guess, the stabilized, especially for both the chlorobenzene intermediate and the anilinium intermediates, because the very electron-rich nitrogen in aniline can donate its electron density, forming an aminium ion, greatly stabilizing the intermediate. This doesn't happen with the intermediate for chlorobenzene, but the carbocation being adjacent to the more electron-rich chlorine does stabilize the ortho and para intermediates relative to the meta-intermediate. From this, the intermediates reacts in the same way with just aluminum chloride instead of ferric chloride, and then hydrogen chloride is off-gassed, aluminum chloride is regenerated, and you get dichlorobenzenes. Thank you for watching. If you want to, like, comment, and or subscribe, and I'll see you next time.